And it's recording. Yep, okay. So I'll try to keep it simple. Okay, try to keep it simple, explain just whatever that is necessary. And of course, the examples that we're going to see today, it won't be extremely tough, but I hope from these simple examples, after this, when we move on to more complicated ones, you can do it. Okay, anyways, new topic, vector calculus, so be ready. Okay, let's start it off. Let me share my screen. Okay, just let me know in the chat. Can you guys see the whiteboard clearly? Any problem? Just a yes or no. Guys, anyone? Just anyone, please. Just want to make sure that it's clear. Okay, okay, clear. So this is like a so-called mind map, right, of what we are going to learn today. Not much. Of course, yes, I will zoom a bit. The only reason why I'm zooming out is because I want to show you the whole picture. But then later on when I'm doing it, I will zoom in a bit. Okay, so vector calculus is an extremely wide chapter. If you look at textbooks on the internet or any textbook, you might even see vector calculus as a whole subject by itself, not even a chapter, as a whole subject. So it's very wide. The one that we are going to look in Engineering Maths 3 is more to certain special areas where you will come across vectors. Of course, we want to list down everything, impossible. So some important parts where you will encounter vectors in engineering mathematics. But before going to that, okay, so let's just first explain to you what is a vector field or a vector function. You will commonly come across these words so many times, so it makes sense to start with this. A vector field, first thing first, vector field or vector function is the same thing. Okay, so don't get confused. Vector field, vector function, same thing. Although it says field, in reality it's just a function of a vector. Now, if you still remember, a vector is anything that has direction and magnitude. Not only you have magnitude saying that, okay, this is 6, but you also have the direction. It is 6 going in this way. So that is a vector. And vector are commonly written in this form, something I plus something j. Okay, usually you have the I direction and then you have the j direction. In vectors, we don't say x and y. We say I and j direction. So if you're dealing with a 3D kind of vector, not only would you have I, not only would you have j, you would also have k as well. Actually, these are just x, y, and z. But in vector, the way we say the axis is I, j, and k. Okay? But although this is a very commonly used notation for vector, I don't prefer it that much because you have to write the I, J, K every single time. For me, a way easier notation, okay, let me write back the same vector here. A more easier notation is simply this. The first number is negative y. Don't put the I because it's understood. Whenever it is the first element, it is corresponding to I. So I would write it simply as negative y and x. Done. I'm not saying this is wrong, this is correct, but I think this is way easier. So in that case, if I write the second vector function or vector field, whatever you call it, it's way easier to simply write it as 2x. The second element is, or second component is negative y. Third component is negative 2x. There you have it. Much more easier. Okay, so for me, I would prefer this. And I suggest for consistency in our class, let's use this as well. Okay, it's not the correct one, but it's the more simpler one. So vector function, you can plot it. You can plot it. You can see some kind of, we don't call it a graph, we call it a field. See, when visually it makes sense to call it a field. When mathematically it makes sense to call it a function. Okay, so let me show you. Of course, I'm not going to ask you to plot it now because it's hard to plot it on a piece of paper manually. However, what I want you to know is that vector function or vector field At every point xy, if I put x is equal to 0 and y is equal to 0, I will get a vector. So at 0, 0, I will get a vector. I'm not sure where it will be pointing, but it will be pointing somewhere. At 0, 1, when I put 0 and 1, I will get a vector. So that vector will be pointing somewhere. 0, 2, that vector will be pointing somewhere. So at every point, there will be a vector. So imagine you're plotting a lot of arrows. So actually, the whole thing you have is a bunch of arrows pointing in different direction. So let me show you how does vector negative y x looks like. I got an application online. Okay, why is this? Okay, where is it again? This is a vector field generator. So I have no idea what all the complicated thing down here means. I just saw that someone made this calculator and shared it for us to use. I'm using it. Okay, I'm using it to plot the vector. So our vector just now was negative yx. So negative y and x. So this is how the vector field looks like. Can you see it's a bunch of arrows plotted together, but once they are plotted together, you can see some kind of pattern there. So this is how a vector field looks like, but without using any software, it will be extremely hard to do it. So let's try one more. This is a two-dimensional vector field because you only have two components. If you have three components, 2x, negative 2y, negative 2x, you can imagine you're going to get a three-dimensional vector field. So let us try to plot this. I also found one for 3D vectors. 2x, negative 2y, negative 2x. Okay. 2x, negative 2y, and negative 2x. And there you go, an extremely weird shape, but still is a three-dimensional vector field. I don't really feel comfortable seeing this. For some reason, it feels so uncomfortable to see this, but you get the point, right? It's a weird 3D vector field. Just now it was way nicer, actually. The simplest 3D vector field I can think of, x, y, and z. Yeah, a standard one. It's pointing in all the direction from the center towards out there. But anyway, the idea is that three component will give you three-dimensional vectors. So, but the key point in this chapter is not to plot any vector field or vector function. Oh, I typed 22x, isn't it? So sorry. Okay. All right. I didn't notice it. So, the point of this chapter is to teach you when will you meet vectors in engineering mathematics. Okay. So, again, today I'm not going to cover every single thing, but two of them. So let's look at the first scenario where you will encounter vectors. One is in the form of gradient vectors. So what does a gradient vector mean? Okay, I really hope that in engineering maths 1, you learn partial derivative, okay? Because I'm only going to quickly recap here. Okay, if you have, whenever you have a function of multi-variable, meaning that in the same function you have more than one variable x and y. If this is true, not only x and y, sometimes you might even have x, y, and z. But the point is, if you have a function of multi-variable, okay, you can find partial derivative, meaning that you can find what is the derivative with respect to x, you can find what is the derivative with respect to y, because there are two directions. If you only have one variable, I ask you to find the derivative, it's simply f prime x. What else is there? There's only x direction. But when you have two variables, it can be x direction, it can be y direction. So that's why you have two derivatives, two different types of derivatives. Partial derivative with respect to x and partial derivatives with respect to y. Okay, so how do you find fx and fy? I believe you have learned it, but I'm still going to recap it. It is very similar to multiple integral that we learned in chapter 1. If you're differentiating with respect to x, y is a constant. If you're differentiating with respect to y, x is a constant. Okay, so how does that work? For example, if you have 6x squared y cubed, a totally different example, right? So what is my fx? Imagine your y cube and 6 are just constant. They are just constant. You can even rewrite them like this, because the whole front thing is just a constant, doesn't even matter. So what do you get if you differentiate a constant x squared? The 2, you push it in front, multiply with this, and then the x reduced by 1, isn't it? So that's how you differentiate it. Just treat your y as a constant. If you're differentiating with respect to y, then your x is a constant. Okay, so that's the basic idea of it. Almost like the counterpart of multiple integral. Nothing much. Okay, so let us try. This is a function. So my partial derivative, meaning that if you want me to interpret it, is the rate of change in the x direction. Meaning that every function is a rate of change, right? Rate of change of temperature, rate of change of speed, rate of change of distance, this and that. How does the function change when I only change the x? So imagine you only change the x direction. So how does the function change? What is the rate of the change? So that is the interpretation. So my sine 5y, there's no x here at all. So that's just a constant. Doesn't matter. X squared, if I differentiate, I would get 2x. So overall, I would get something like this. 2x sine 5y. Why nothing happened to the sine 5y? Because it's just a constant. There's no x in it. Okay. So what if I want to find fy? Then your x squared is just a constant. So x squared is just a constant. What do you get if you differentiate sine y? Sine, if you differentiate, you get cos y. So cos 5y. Chain rule, remember, because inside here it's 5y, multiply by 5. Or maybe I would just prefer to put the 5 in front here. It doesn't matter, you put it in the front or you put it at the end. But if you differentiate sine 5y, you get cos 5y times 5. So this is your fx and fy. The gradient vector, okay, now we come to the vector. The gradient vector of a function f is the vector containing fx and fy. So the collection, because whenever I have a multi-variable function, I ask you what is the derivative. There are two types of derivative, right? So the collective information of these two gradient is the gradient vector. So the final answer would be something like this: 2x sine 5y, 5x squared cos 5y. So this is your gradient vector. So when you combine both of the components, it becomes a vector. Of course, you can try to plot this vector and see how it looks like. But the idea is you are seeing a vector as the final answer here. This vector will be used for so many other purposes when you learn other modules, higher modules after this. So gradient vector is a very important concept. Okay, just to see whether you guys are getting this or not, now, you see, actually there's supposed to be a fz, right? But in this case, there's no fz because there are only two variables. So if you have three variables, then of course, you have fx, you have fy, and you have fz. So I'm going to give you one function, a very simple one, not even complicated. Try to find what is the gradient vector. If any of you don't have paper right now, go and take your paper. It's a small one, but I think it makes sense for you to try this out first before we go any further. So what is the gradient vector of f? Let me know if you have any problem. I'll give you some time, but try it out. Try to warm up a bit. So I don't need to see your solution, just let me know the final answer that you get here. Oops, sorry. Okay. If any of you are stuck, please just let me know, right? Don't be reluctant to let me know that you can't follow along, because otherwise if I jump into further subtopics, then you'll be very lost here if you want to cover back. So I'm not sure because you're not saying anything, but just a help maybe, I want to do one of the partial derivative, fx, to see whether you guys are in the same path or not. Okay, fx means you keep x as the variable, everything else is constant. The y is a constant, the z is a constant, only x is a variable. Okay, all right, so z is a constant, so the constant is not even affected, it's in front here. E to the power of negative xy, you differentiate e, you will get e again, e to the power of negative xy. But do you remember chain rule? What does it mean by chain rule? For example, if you have e to the power of 2 negative 2x, if you differentiate this, you would get e to the power of negative 2x again, yes, times with negative 2. Do you still remember that? You have to times with negative 2 again. So same here. You're differentiating with respect to x. So you will get e to the power of negative xy again, times with, differentiate the constants around the x, which is negative y. So therefore, let's see if I bring the y in front, it's going to be negative yz e to the power of negative xy. So that is my fx. Okay, basic chain rule, and the z is untouched because it's just a constant in front. Can any one of you share me your final answer? I don't expect it to be correct, of course. Just want to see some kind of effort on doing this. Right. I wonder why. Why are you still doing it? Okay, it's fine. Let me at least know whether you get the answer or not. Let me just give you a yes or no. Just let me know whether you got it. Now I see there's a bunch of answers coming up. All right, let me check it out. As for the rest of you, all right, so did a poll, but anyways, let me check the others. Starting from, okay, we have Liz. Yes, correct. Liz Wong is correct. Yihan, oops. There's a negative missing maybe, is it? Okay, I think even List was missing a negative. For the exponent, there should be a negative, right? E to the power of negative xy for the first part. But I guess the partial derivatives are correct. Okay, I never thought that looking at exponents in the chat box will be this messy. But I do get more or less the same answer, except the negative and positive might miss out a bit. Fu is sending something here. Okay, let me check what I got. Yes, I got the exact same answer that Fu Meaning is sending here. So if any of you get the same answer, then it should be correct. This is what I got as well. Like Felix is also correct. Yes, okay. So Aiman is asking me why negative y? Which part, Aiman, do you mean why negative y? Okay, let me just show it anyways in the whiteboard. Oh, do you mean for my fx, why do I get negative y? Or here, why I multiply negative y? It's because the thing, oh, there you go, done with the whole solution, is it? Okay, yes, correct. So the negative y is because when you are using chain rule. So everything beside, it's more like, what do you get if you differentiate negative xy? You will get negative y. So that is the thing that you multiply. Oh, it's just the answer there, but it looks so, I see, yep. Okay, so moving on. So I can see that some of you did get it. I didn't check the poll though, what happened? Oh, 17 of you, yes, nice, which means we can move on. All right, so not going to do it more, but you get the idea, right? If you have three components for the vector, then it will be, if you have three variables in the function, then it will be three components in the vector. Two variables in the function, two component. Okay, a very simple one. But unfortunately, the functions won't really be easy all the time. But for the class, let's use easy examples. But during your practice, I will give you more harder problems. Okay, I don't want to discourage you now by giving you all the hard examples. Okay, the key today is to just learn. And directional derivatives. Okay, from where do I start? What's the time now? 9:11. Okay, this should be fine. After we are done with here, let's have a break and then continue with some practice problems. Okay, all right. Directional derivatives. So where should be good to start? Just now, we are doing gradient vectors, isn't it? I told you that if you have a multi-variable function, fxy, for example, you can find out what is the rate of change or what is the derivative in the x direction. Meaning that what happens if you keep y, don't change y. If y is equal to 2, stay at 2. But x, you keep on changing it. So when you only change x, what is the derivative? That is fx. If you only change y and you keep x as a constant, that is the rate of change in the direction of y, or fy. Now, what if I want to change x and I want to change y at the same time? Now, that is already a more complicated question. So, but there is an easy way of doing it, fortunately, all right? So the whole point of learning directional derivative is that what if I want to find the derivative in totally another direction, not x, not y, but somewhere in between where both x and y changes. So then, for the sake of illustration, I actually presented all four vectors here because I have a reason. I want you to think about this. Let's say I have a function, right? I have a function f, and I want to ask you, what is the rate of change of that function if I want to change both x and y such that I want x to change twice as y? This is my question. I want x and y both to change, but in what pattern? I want it to change in a pattern that x is changing twice as y. So now, you can see that if x is changing twice as y, okay, you can actually, along the graph where x changes twice as y, we have the vector 2, 1, isn't it? In 2, 1, can you see x is 2 times the value of y? So this is one vector which describes my condition. X is changing twice as y. Okay. However, this vector is also describing my condition. 1 over 5 is 2 times 1 over 10. So again, 6, 3 is also describing my condition. My x is twice as y. This is also describing my condition. Although it might look like a bit complicated because I have square root, but this times 2 is this. Okay, so that is to say there are infinitely many vectors that can describe the condition that I want here. So which am I going to choose? Because if I choose different vectors for my calculation, I'm going to get different answers. If all the mathematicians around the world get different answers, how can they compare with each other? Because it's not consistent. So for the sake of consistency, we are going to choose one. So out of all the infinitely many choices that describes my condition here, the one that I am going to choose is unit vector. So this is for consistency. So everyone agree. Out of all the infinitely many choices, let's use unit vector. Okay, unit vector, if you forgot what's the meaning is, unit vector is any vector with magnitude 1. For example, if I compute the magnitude of this vector, 2 square plus 1 square is 5, so square root of 5. Can you see it is not equal to 1? So this is not a unit vector. This is not a unit vector, this is not a unit vector, but if you compute this, you will see that it is a unit vector. So let me compute. This is going to be, this square is going to be 4 over 5. This square is going to be 1 over 5. So 5 over 5, the square root of it is 1. So now, if the magnitude is equal to 1, the way you write magnitude in mathematics is something like this. This is how we write magnitude of vector v. Anyways, if you get it is equal to 1, it is a unit vector. So this is my choice. Okay, so hope you get it. I will show you how to find unit vector in a while. Now, so I've already chosen unit vector, but for what? I am choosing unit vector to put in inside this formula. This is the formula, right, to find the directional derivative, which is just another fancy way of saying the derivative in the direction of the unit vector. So this is the derivative where both x and y changes, but changes in what pattern? It changes in the pattern of my unit vector. In this case, 2, 1, twice as the value of y. Okay, so whenever you hear this word, find the directional derivative in the direction of whatever vector that they give. This is the formula. Okay, so I'm going to give you one example now. Let's look at this. So find the directional derivative in the direction of unit vector u. Can you see? U means the small u here is the unit vector in the direction of this. It's the same vector that we just did. So from the test, first of all, I have to check the vector that they give. Is it a unit vector? So when I compute the magnitude just now, right, it's the same vector up here. When I computed the magnitude, I found out that the magnitude was not equal to 1. So therefore, this is not a unit vector. So I have to find what is the unit vector myself. So how do you find the unit vector by yourself? The unit vector is simply this vector, right? It's simply the vector divided by the magnitude. That is the, oh my god, why does it change to a triangle? Okay, divide by the magnitude. So this is the formula to find unit vector. So the vector itself is simply 2, 1. The magnitude I already computed up here. I got square root of 5. So dividing both of these things, that is your unit vector. Of course, a nicer way of writing it, instead of leaving it like this, is just divide each of the component by square root 5. So you're going to get 2 over square root 5 1 over square root 5. Okay, this is your unit vector. Once you find out what is the unit vector, then you can use the formula shown here. So according to that, the directional derivative in the direction of u is gradient vector dot product with unit vector. So apparently I need my gradient vector, which I just learned just now. So let me find the gradient vector first. The gradient vector is, okay, what is my fx? This is my function, ax cos y. Okay, x cos y, if I differentiate with respect to x, the cos y is just a constant. So constant x, if you differentiate, you only get constant. Okay, if you differentiate with respect to y, cos y, if you differentiate, you will get negative sine y. So multiply with the x in front here, negative x sine y. Okay, this is my gradient vector. So dot product with my unit vector. My unit vector is 2 over square root 5 and 1 over square root 5. So I've already plugged it in inside my formula here. Just left to compute it. In case if you have forgotten how to compute the dot product is very easy. It's just the first component multiplied by the first component plus the second component multiplied by the second component, and so on. So in this case, it's just cos y multiplied by 2 over square root 5. So I don't want to simplify it because it's impossible anyway. Okay, plus second component times second component. So that would be negative 1 over square root 5 x sine y. Okay, so that is dot product. Very easy. Okay, first component multiply with first component plus second component multiply with second component. And of course, we know positive and negative becomes negative. So why not just write a negative? So this is my directional derivative. This is my gradient, or this is my rate of change when I allow both the x and y to change such that x changes twice the value of y. I know it's so much to comprehend, but this is how you do it. You can simply boil down to two steps. Just find the unit vector, the first step. Second step, find the gradient vector. Third step, find the dot product between them. Okay, so it is 2 over square root 5. Oh, yes, thank you very much. It's 2 over square root 5, correct? Okay, so three steps. Find your unit vector, find your gradient vector, find the dot product between both of them. Okay, so that would be your directional derivative. So, three steps. Let us try one example. Try to zoom in a bit. Oops. Okay. So, try to do the question down here. But this one is a bit more extra. Can you see they ask you to find the directional derivative of a function at a point. So, at a point, this part, just leave it first. Just leave it. Just find your directional derivative as usual. You have a function, you have a vector. So find it as usual, but whatever answer you get finally, then put x is equal to 1, y is equal to 1, z is equal to pi. Just substitute the value at the very final answer. So instead of getting an expression like this, right, like the one down here, you will actually get an answer, you will get a value. So try that out. Find the directional derivative and then plug in the coordinates here. Take some time, try it out. There are three steps involved. Right, so please carry on. I just want to spend some time to find to check whether this is a unit vector. If not, then I want to find the unit vector. If any of you got the answer, let me know in the chat box, right? So I'm doing the partial derivatives here. If you want, you can cross check. Any signs so far? Anyone getting closer? Alright, there we have it. 3 minus pi over square root 3. Yes, correct. That is the answer, correct. Your answer is this. Let me just write it here. You would have gotten 3 minus pi over square root 3. Yes. Nice. So how about the others? Because once you find the unit vector and then the gradient vector, dot product is very easy. You're just writing side by side and then add all the things together. So and then finally plug in the value there. What value? This value. You have to plug in this value at the final part. 1 pi. When you differentiate ln with a constant, it becomes nothing. Ln with a constant. Differentiate ln with a constant. Do you mean what do I get if I differentiate something like this? Ln 2, for example? Then yes, it becomes nothing because there's no x, there's no y. It becomes completely nothing. Oh, I see why you're asking this question. Because yes. So the rest of you just take note that the answer that Chan Jing Hoon gave just now, 3 minus pi over square root 3, that should be the final answer that you get. Or maybe some of you write it separately, 3 over square root 3 minus pi over 3. Not a big deal at all. It's fine. And maybe another reminder, because some student from another class of mine did this mistake. At one point, you need to put in your z to be pi, right? So I believe that you will get things like cos pi at one point. So when you plug in inside your calculator, don't put it as cos pi because I think you will get a bunch of decimal places. What you need to do is convert the pi into degree first. Aiman, okay, how you get the final answer? Alright, right, since there's already a question, how we get, I cannot do it here. Okay, first thing first. My third step is gradient vector dot product with the unit vector. So my gradient vector is the whole thing I got on top here. So let me just rewrite it. 2 over x z cos yz and a y cos yz. Dot product with the unit vector that I got here, 1 over square root 3, 1 over square root 3, and negative 1 over square root 3. Okay. Sorry, it's a bit messy. Anyway, so if you find the dot product, it's just the first component multiplied by the first component. So I will get 2 over square root 3x plus second component multiplied by second component 1 over square root 3 z cos yz plus third component multiplied by third component. Okay, positive and negative is going to be negative. And then I have a y cos yz. All right, so there you have it. So this, is there anything I can simplify? Nope, I can't simplify anything. So next I put in my coordinates 1, 1 pi. According to the question, 1, 1 pi. So my x is 1, y is 1, z is pi. So putting, okay, this is x. X is equal to 1. So the whole front part becomes this. Okay, 1 over 3. Z is equal to pi. So it becomes pi. Cos yz. Y is 1, z is pi. So it becomes cos pi. Minus y is equal to 1. So no changes. But the cos, y is equal to 1, z is equal to pi. So 1 times pi is pi. So this is what I have to try to solve. So the 2 over square root 3, just keep it there. Nothing much for the moment. The pi, let me put it up here. Just a rewriting. Okay, cos pi. Cos pi, if you change pi into degree, is going to be times 180 divided by pi. That's how you change from radian to degree. If you want to change from radian to degree, multiply 180 divide by pi. Sorry, why did I put a 5? Divide by pi. So if I do this, it's going to be cos 180. Cos 180 is equal to negative 1. Okay. And then again, cos 180 is negative 1. Can we leave in decimal? Yup, completely fine. You can leave it in decimal. So 2 over square root 3 plus, sorry, not plus, it becomes a minus, minus pi over square root 3 plus 1 over square root 3, and therefore you get the final answer is 3 minus pi over square root 3. Decimal answers are completely fine. Pi is also fine. Decimal places, at least take 2 decimal places to make sure it's kind of accurate. Okay, Aiman, no problem at all. Okay, so with that said, the time is 9:36. Let's have a break. We'll continue back at 9:50. Okay, just a bit more exercises, not going to continue until 11, maybe 10 plus a bit, but just a few exercises and then we call it a day. Okay, so we'll meet back at 9:50. Yep, 9:50 then. Let's meet back 9:50. Oh, yes. Thank you very much. I muted my mic just now because we're having a break. I just wanted to make sure that everyone is here. No one left the meeting, but I'm not sure whether everyone is in front of your devices right now or not. The participants list is full. Okay, let us just wait for a minute, make sure everyone is back. Okay, so I'm going to assume that everyone is here. No more new subtopics for today. We're just going to do more, not more, three exercises on whatever that we have learned so far, gradient vectors plus directional derivative. So while you are taking a break, I actually find on the internet a bunch of questions. So I'm going to share the questions right now and let us try. Hopefully by trying this question, you get a bit more better on finding partial derivative, this and that. So let me share my screen. Okay, so there you go. I have three questions, 1, 2, and 3. Everything related to what we have learned so far. So let's start off with this. I want you guys to try it out before I even show you how to do it. Okay, so three questions. Let's start off with this. Find the gradient vector field, something that we have just learned. Any questions, please ask me. This is not a test, all right? This is just a practice. Please ask me if you have any questions, if you forgot how to differentiate something, you forgot how to do something, you're not sure, you can either ask me directly through by using your mic, or you can also put in the chat box there. Okay, so I don't know what do you mean decaffeinate? I assume you don't know how to differentiate ln xy over z. Okay, you have a ln xy over z. May I know you are trying to currently differentiate with respect to what variable? Is it x, y, or z? Because z is down there, xy is up there. So give me one variable. You are trying to differentiate with respect to what? X. Okay. So maybe xy over z is what is confusing you. But how about, for example, ln, just saying x. Okay, let's say ln 2x. How would you differentiate ln? Ln, if you differentiate, you will get 1 over everything here. 1 over 2x. And then chain rule, multiply by differentiate 2x. What do you get if you differentiate 2x? 2. So that's how you do differentiation of ln. So in this case, right? So if I differentiate ln of xy over z, I'm going to get 1 over everything here. And then I have to multiply with what do you get if you differentiate xy over z with respect to x. Now I told you y and z is just a constant. So this is like actually differentiating 2x over 5. The y and z is just constant. So what do you differentiate? What do you get if you differentiate this? You just get the constant. So same here. What do you get when you differentiate everything else apart from the x here? That is the thing that remains. So y over z. So 1 over a fraction is equal to the upside down version of the fraction. So this would be z over xy, and this remains. So from here, let's see what can I simplify. Z and z, y and y. So what remains is only 1 over x. So that is how you would differentiate that. Hope it's a bit clear, although it's kind of confusing. The key point is 1 over everything inside the bracket multiply by what do you get when you differentiate the thing inside the bracket. Chain rule. What we are doing here is called the chain rule. You can Google for it if you want to know more information. Yeah, the z and y looks like something that is involved but is not. Because when you differentiate respect to x, the z and y are just numbers there, they are just constant. Alright, you're welcome, Ibrahim. So if you already got the answer, it's just that you're unsure to present your answer because it might be wrong. Let me show you the final answer. Just see whether you get the same thing or not, because I took it from the internet anyways, and the solution is there. We are currently doing this. Yep. So did you get something like this? Is it the same question? Yep. Oh, the question. Right. This was the question. Can I show both of them on the same part? Okay. So I can't see the chat box if I'm doing it like this. How to get -1 minus z for the last part, is it? Okay, let me try it out. Okay, let me check. Give me a moment. It's, okay. The power of z, which is -1. Yes, we already have an answer. That is correct. That is the reason why we are getting that. But anyways, let me show you how it works. Okay, so back to the whiteboard. If I am differentiating this with respect to z, then of course ln of something is going to be 1 over everything there, multiply by differentiating the thing inside here. So xy over z. Xy over z, or it can be rewritten as xyz -1. I just bring the power in front. So if you differentiate this with respect to z, the -1 goes in front, and then the power -1 again, so it becomes this, or in other words, -xy over z squared. So this is the thing that you get once you differentiate the thing inside the bracket. So put it here. Okay, and as I told you, 1 over a fraction is the fraction upside down, so it's going to be z over xy, and then here it's -xy over z square. So xy cancel, z and z cancel, -1 over z. So I hope the others who still can't get it a bit more clear now. The key is to actually rewrite the over z into z to the power of -1. So it's a bit easier to differentiate. Okay. All right, no problem, that mean. So yeah, maybe that was the hard part because you have a lot of something, but then the something is not in the numerator, it was in the denominator, so a bit tricky. But if it's in the denominator, just bring it up and make the power negative. That should solve the issue if you come across similar thing in the future. Okay, so that was the answer. And for the others, try it out if you're still stuck on it and let me know. Let's try one more on gradient vector, but this time around you have three variables, x, y, and z. Okay, you have x, y, and z. Let's try this out. So now you don't have ln, but now you have trigonometric function, x and cos of x, y. Now, you just notice even the fx is already slightly complicated than the previous one, isn't it? Because you have an x here and you have an x inside the cos as well. So don't forget, whenever you have two x side by side, there's an x here and there's another x here, you must use product rule. Okay, product rule is u v prime plus v u prime. Hope you still remember. If you have 2x up and down in the form of a fraction, let's say you have an x here and you also have an x somewhere around here, then you must use quotient rule. Quotient rule is vu prime minus uv prime over v square. Okay, so this is quotient rule, this is product rule. Right now there are 2x side by side, so you must use product rule then, where your first thing is your u and the second part is your v. So again, let me show you the answer and see whether you can get the same answer here. Only the first one is a bit long because you have product rule in it. Is it this? Yup. Okay, it's a long answer, but there you go. There are three components separated by a small comma here, so make sure you are aware of that. So three components, one for X, one for Y, one for Z. Yes, yes, sure. I can send you the link for the solution. Why not? Right now, do you need it right now? Um, this is for the second one. Okay. So there you go. That is the solution for the second one. Okay, so let's do one more. The last question for today, which would be on this. A step from gradient vector, which is directional derivative. So you have one extra step. Remember, not only you have to find the gradient vector, you have to find the unit vector as well, if the given vector is not a unit vector. And then you find the dot product of both of them. So let's try one last thing for today. Clearly the vector v is not a unit vector here. The numbers are quite big, so you have to find the unit vector yourself. The answer for the previous question, Dinesh, can you see a link there in the chat box? That was the link to the solution for question number 2. So unless you mean question number 1 that is way back, yes, you can refer to that. Okay. Oh man, why did I put square root of 5? I think my mind is somewhere else. Thank you for correcting me. It should, because I think I keep on thinking the square root 5 that we got way back during the example just now. Yup, 3/5 and -4/5. Thank you guys. So if you are currently doing the dot product, once you find the gradient vector and the unit vector, just make sure that the gradient vector is correct, okay, so that you don't do all the wrong steps afterwards. Your gradient vector should be, yeah, this. Not yet complete, but this is just your gradient vector. So this is what you are going to dot product with the unit vector later on. Just take note of that. So always remember to use chain rule. Like, of course, if you differentiate cos, you get negative sign, but then you have to further multiply with what do you get when you differentiate the thing inside the bracket. So that's where the -1/y, the x/y square, that's where they come from the chain rule part. Okay, so I think you guys are past this stage, but if you are still doing it, carry on. For those who are almost to the completion there, after you dot product everything, you would get this. Oh, yeah. Actually, on the right hand side, they already simplify it, but it's not necessary to simplify it. The version on the left here, this is just fine. Okay, this is just fine. But if you want to do it some kind of simplification, then go ahead. Yes, yes, I can send you the link. Perhaps it is more convenient for you to look in your device. Oops. Okay. Right, so again, the directional derivative part, it is only slightly complicated in finding the unit vector and the gradient vector. Once you got them, dot product is way easy. Component multiplied by component plus component multiplied by component and so on. So that's not the hard part. Okay, so just keep in mind what we have learned so far. Not much actually, not much. The only thing that we did was, I see a happy ton here. Did you get the correct answer? So the only thing that we did today was an introduction to vector. We try to plot some vector field. I will share you the link on how to plot the 2D and 3D vector in case you are interested. Just type in your vector then and take care of everything else. But more importantly, we did gradient vectors and directional derivative. So that's all for today. Okay, the time is 10:25. Let me show you your QR code so that you can sign up for your attendance. And I will be sharing the whiteboard. So yeah, no worries on that. Okay. Lecture. Okay, there you go. You can sign up for your attendance. All right, we have 4 absent so far, but let's just give a few more seconds. All right, so I don't think, oh, I just about to say the thing is not moving and it's already moved. Okay, so in case if you can't sign up your attendance, just let me know. I can actually download the attendance sheet from the meeting itself. There is such an option, but just let me know if you have any problem, right? We can sort it out. And as for today, oh, there's something in the comment. What is it? Why Fy is equal to that? Okay, a very quick one just before I end the class, since we have a question here. Why Fy is equal to that? Where is Fy? Okay, so if you differentiate cos, okay, if you differentiate cos, you're going to get negative sign. And then you have to multiply by differentiate the thing inside here. So if you differentiate x over y, I can write it like this, which if I differentiate, I will get negative x, y, negative 2. This part is what I'm going to multiply here. Yes, Tan has already mentioned that as well. Okay, so that is where negative and negative become positive, but then you have an x over y square. Okay, so try that out. Anyways, for the rest of us, we are done for today. So see you guys in next class then.
Thank you,
Well,
sir.
okay, bye-bye.
Thank you, sir.
All right,
Thank you, sir.
welcome.
Thank you, sir.
All right, sure.
Thank you, sir.
Welcome.